Hello, everybody. Hope you can all hear me okay. Thank you for joining us and welcome to Ray Castle's live webinar looking at the K factor in microwave link planning. During this webinar, we'll be exploring the K factor and discussing its role in calculating path clearance, identifying reflection areas, and optimizing antenna spacing in diversity systems. The webinar will be delivered by Carl van Heeswich. Carl is a highly experienced trainer who has presented courses for our customers live online and in many locations around the world. He's a radio specialist whose expertise extends across a wide range of telecommunications technologies. These include radio theory, point-to-point, point-to-multipoint, and mobile systems. Before we get onto the webinar itself, I'd just like to give you all a brief introduction to Ray Castle for those who aren't familiar with us. We're founded in 1958. We initially specialized in radio and maritime communications. We began training in telecommunications during the early 90s and have since established ourselves as a leading training organization in this field. Extensive portfolio of courses cover all the major telecoms technologies. We use a variety of delivery formats from traditional classroom classes to live virtual sessions such as this one and on-demand distance learning courses. During the past 60 years, we've trained over 300,000 industry professionals from all parts of the industry and across the world. And we are the preferred partner to many telecoms industry giants, and you'll see just a handful of those below. So what's new at Ray Castle? Recently, the company was acquired and we are under new management now. So lots of new names, lots of new faces, and lots of new energy. We've had a busy past 12 months. We've made good use of lockdowns. We've launched our new Enterprise Online Academy, providing access to all of Ray Castle's learning pathways to all employees within an organization. We've expanded internationally, including the sale of our first online academy to a mobile operator in Asia. We've launched a new consulting division. We've introduced a mini MBA in telecoms, extending our training reach to cover the business of telecoms, including management, leadership, and business model development. All our courses are also now available to purchase online, giving you immediate access to the training you need. And if you want to find out more about us and our training courses and portfolio, you can visit our website, raycastle.com. And here are just a few of the faces from around the company. You'll see key members of our management team and our senior training team here. If you'd like to contact any of us about anything, please do so at the email address below. Okay, so I think we're now ready for the webinar itself. Just a bit of housekeeping. Could you all please put your mics on mute for the time being? I'll just make it a little bit clearer for everyone. The presentation will last approximately 45 minutes. If you have any questions, please post them in the chat box and Carl will answer them at the end of the session. Now I'd like to hand over to Carl for the presentation.
Thank you, Paul, and welcome everybody to this presentation on the K factor. That's what I'll be talking about today and its relationship to the whole process of microwave link planning. What we're actually planning ourselves, funnily enough, is a sequence, a series of these sort of webinars entitled Insights into Radio. So this really is number one of a series we're planning on putting together. And this first one, as I say, is talking about the K factor. What I will be talking about is the impact of the K factor, the role it plays in determining path clearance on a microwave link, identifying reflection areas, and the role it plays in calculating antenna spacing where space diversity is required. So the focus of this really is on microwave link planning. So what I'm now going to do is I'm now going to jump out of this slide deck, move on to my desktop. I suppose we all sometimes experience that, and dive into the microwave link planning course that we offer here at Ray Castle. So obviously the course itself has multiple sections. We look at availability and performance, reliability, objectives, how you calculate those, antennas and so on. But as this is about the K factor, we're going to start here by relating it to, I guess, what we most associate it with as radio planners, which is path profiling. So I'm going to dive into this section of the course, pick through the relevant slides, and cover the topic that way. Okay, so here we go. First thing I'd like to point out is the link planning process is multiple stage process. We go through these steps. Any link planners out there will be aware of some of these steps. I think there's a microphone on somewhere. If anybody's got a mic on out there, could you mute it, please? That would be very much appreciated. Multiple steps, some iteration in the various steps, but K-factor relates to, realistically, this point of the process, this stage of the process, where we're trying to determine tower heights and antenna heights, and indeed the feasibility of the link. Will the two radio antennas at either end of the link be able to see each other in radio terms? Can I establish a connection between these two antennas? Is there anything in the way? Can I clear obstructions? And that is, in essence, the profiling process. Determining tower heights, determining antenna heights, and determining the feasibility of the link from a clearance perspective. Okay, what I'm now going to do is jump to this slide here. Now then, our radio signal is going to propagate through the Earth's atmosphere. Now, those of you who've been radio engineering for some time, either mobile coverage planning or link planning, will be aware that the medium we use to carry our radio signals in the Earth's atmosphere is, of course, a natural medium. Now, being a natural medium, it is not stable. It doesn't behave consistently in one particular way. So the atmospheric conditions change over the day, over an hour, over the seasons. Now, if you can recollect your physics lessons at school, you might remember things like refractive index of a medium. And the refractive index is denoted by a number. Now, if the refractive index of the medium was 1, then an electromagnetic wave propagating through that medium will travel in a straight line. It will not refract. It will not bend. It will not curve. It will travel in a straight line. Now, as the Earth's atmosphere is not a stable medium, the conditions of that medium will change. And what that will cause is a change in the refractive index. So sometimes, in a quite simple model here, the higher altitude air will be thinner. Can I put it that way for now? I'll dive into this a little bit deeper shortly. And the lower air will be thicker. And this, of course, will cause a bend, a refractive element in the radio's signal's propagation. It will bend towards the Earth. And we consider this sort of thin air above, thicker air below. We consider that kind of normal conditions, and that will create a degree of refraction of the radio wave. Sometimes those conditions will change, though, and we get some strange abnormalities, in which case the thicker air can be at the top and the thinner air can be at the bottom, in which case the radio trajectory, the refraction, will trend towards the upwards. So you can imagine if you have two radio antennas, one at each end of the link, then the trajectory of the radio beam between those two antennas will be bending, refracting to a degree, up or down, and that will fluctuate through an hour, through a day, and across the year. And as radio planners, we need to manage that. We need to incorporate that into our calculations. Now, I'd like to draw a small distinction here between the scientist and the engineer. And if there are any scientists out there, I'm not decrying anybody or hopefully not insulting anybody. But I would suggest to you, and I don't know if you agree with me on this, but the engineer is trying to take the scientific knowledge and create a model which will help him calculate as a best educated, very educated guess as to whether the link will perform adequately or not. So we're dealing with these scientific criteria in a kind of a practical engineering way. And we have to factor this in to our link planning process. So I will now jump to the next slide I want to talk about. And I did mention that we would talk here about a little bit more depth about these atmospheric conditions. So I'm going to rest on this slide for a few seconds to illustrate a couple of things. In this graph here, this middle graph here, that I'm just sort of highlighting now, this is temperature, air temperature, and we can see that falls with height through the Earth's atmosphere under normal atmospheric conditions. This is air pressure, and that falls not linearly, non-linearly, with altitude under normal atmospheric conditions. And this here is humidity, or water vapor pressure if you prefer, and that also falls with altitude in a slightly different way to the other three. So I'm just raising that issue now, okay? It's air pressure, air temperature, and humidity. Now let me go back a slide. Now, as I've mentioned already, that if the refractive index of a medium is 1, then an electromagnetic wave propagating through that medium would travel in a straight line. Now, interestingly enough, the value of n for... All right, Dorit, stop it there, I'll start again. I'll start again. I just need to change something. Okay, starting from here. Sorry, starting from here. Now, as I've mentioned previously, if the refractive index of the medium, such as a vacuum or any medium the electromagnetic wave is propagating through, if the refractive index of that medium is 1, the electromagnetic wave will travel in a straight line. Now, our radio signals are propagating through the Earth's atmosphere, and we need to know what the refractive index of the Earth's atmosphere is, and as I've mentioned already, it will vary due to meteorological conditions. Now, I've annotated the diagram here down below, bottom left here, to show you the mean value of n around the planet is 1.000315. Now, the important point to note here is it is not 1. Therefore, an electromagnetic wave propagating through a medium with a refractive index of 1.000315 will not travel in a straight line. There will be some degree of refraction of that electromagnetic wave. Now, because the Earth's atmosphere isn't stable, it's impacted by meteorological conditions, then this value of n here, the mean value, as it's the mean value, we know it must be sometimes below that, sometimes above that. But the important point to notice here is it's this value here that changes. This could go up to 420, it could go down to 490, but it's always 1.000 something. So in other words, this 1.000 doesn't change. It's just these last digits here that change. Now, radio engineers don't like awkward numbers like that. We like to kind of simplify things where we can. So we just play a little mathematical trick with the formula above that, the little piece I've annotated there. And we work in units of refractivity, dimensionless units of refractivity denoted by capital N. And all we do is delete the 1.00 and just use those last few digits. So to us, the mean value of n, capital N, units of refractivity, is 315. We do away with the irrelevant almost 1.000 part of that number. Now, the formula on the right shows you how we can calculate that value of n in units of refractivity. at any location on the surface of the Earth. What we need are, though, we need these three values. We need to find out what is the atmospheric pressure, what is the air temperature in Kelvin, what's the water vapor pressure or humidity, and again here, temperature in Kelvin. So once we find out those four values, or we know what those four values are, we can place them in the formula and we can work out N for that location on the Earth's surface at that particular time. But we know the air pressure, the water vapor pressure or humidity, and the air temperature aren't constant. So we should expect very much to see this value of N vary over an hour, over a day, over a week, over a month, over a season, over a year. It's almost constantly varying because there must be slight variations in these values all through the day. Now, the map you see before you there is produced for us by our good friends at the United Nations, specifically at the International Telecommunications Union Radio Communications Sector, the ITUR, and is published in one of their recommendations, P.453. Now, these recommendations are freely available from the ITU website. All you need to do is go to ITUR, open up publications, and in there you'll see recommendations, and then you can find the propagation recommendations, the recommendations regarding propagation. They all begin with P dot some number. Now, they produce these maps in that document, P.453. So thank you for them for allowing us to show it to you. And they are published for different times of the year. So they publish maps for different times of the year. I think this one is February, but don't quote me on that. And if we have a quick look round, though, we can see here, look, that in the UK, N will be somewhere around the 340 value. In the Indian Ocean, something around the 400 value. And in Central Australia, something around the 300 value. And we would expect to see variations like that, would we not? So in February, in the UK, it's going to be pretty cold, pretty damp, etc. In the Indian Ocean at the same time of year, it's going to be quite warm, quite humid. And in Australia, of course, it's going to be very hot and, of course, very dry in Central Australia because it's summer there at that time. So you can see these variations in N across the planet. So I hope that makes sense. And I shall now move on to the next slide. Okay, so it's not the absolute value, though, that is of concern to radio engineers, not the absolute value of N. What is the main concern to radio engineers is the gradient, the change in N with altitude. Now, once again, I must stress here that this graph here is talking about what we call a standard or normal atmospheric conditions, when the atmosphere behaves like those related to those graphs I showed you earlier about temperature, air pressure variation, and water vapor pressure. So if it was 340 at the Earth's surface, it would fall to 300 by the time we reached 1,000 meters. So over that 1 kilometer of the Earth's atmosphere, okay, it's a linear fall in N under normal atmospheric conditions of about 40 units. So we decrease the value of N by 40 units over that 1,000 meters vertically through the Earth's atmosphere under standard atmospheric conditions. And that creates this refractive impact on the radio's signal. So let's now look at what actually happens to our radio signal as it propagates through the air over the Earth's surface. Now, what we see here is I'm indicating the trajectory of the radio wave over the surface of the Earth. So here's the curvature of the Earth, the real Earth's curvature, and I've marked on the graph on the chart here the Earth's radius, R there. I'm just picking a value of N at random. I'm just saying that the radio wave is curving like that. That's the trajectory of that radio wave. Now, if I wanted to plot this clearance to make sure I'm clearing this profile, to make sure I'm clearing any obstacles in the way, I have a number of options available to me. So the first thing I could do is I could plot the Earth as a flat surface, like so. The Earth is a flat surface. And then say, okay, I'll put my towers in place, like so. Simulate my towers. There they go. There's my 2 towers. And I'll draw the radio trajectory as a straight line. Now, hopefully some of you will have seen my big mistake, because what's actually happening in reality is I have 2 curves. I have the curve of the Earth and I have the curve of the radio trajectory. And I put some figures in here, as you can see. So just say that was 15 meters, this was 10, and that was 15. If I was to say the Earth is flat and then plot the curvature of my radio signal across that Earth surface there, which I've said is flat, right, then I would have to draw the radio trajectory like this, right? It would sag downwards and then curve upwards to maintain that true relationship of 15 meters there, 10 meters there, and 15 meters there. That should be a smoother curve, of course. So if there was an obstacle in the middle of that path trajectory, let's say there's an obstacle there, I would think I cleared it by drawing these 2 as a straight line. But of course, the curvature of the radio trajectory is really downwards and then upwards here. And of course, that becomes an obstruction to my radio link. So what do I do? How do I plot this? Well, we like to plot the radio trajectory as a straight line. It's intuitive. It's intuitive to plot it as a straight line. We believe radio signals travel in a straight line. But if I want to plot it as a straight line, can you see I'm going to modify the curvature of the Earth? I have to modify the curvature of the Earth to maintain that true relationship, 15, 10, and 15 meters in my example. So how do we do that? Well, what we do is we actually calculate something, which is what this conversation is all about, called the K factor. We actually calculate this value called the K factor. Now, this K factor, we take these 2 numbers, 157, 157. The origins of those I haven't really got time to go into, but it's related to the curvature of the real Earth. Okay, it's calculated from the curvature of the real Earth. And then what we do in this part of the formula here, we add this value of n, the gradient of the value of n, the rate of change that I showed you on that previous graph. So in our case, that value, if you remember, was minus 40. Minus 40 n units goes in there into the formula there. So that's minus 40. That's the rate of change of the gradient of n. I'll tell you what I'll do. I'll quickly go back to that diagram and then we can remember, oh yes, there's a fall of 40 units over 1,000 meters. So that fall of 40 units, we then place in this diagram and whoops, beg your pardon. And we can place in that formula there. And if you divide 157 by 157 minus 40, in other words, 157 divided by 117, the answer is actually 4/3 or 1.33. Now, those of you who've been engaged in link planning using K factor, that'll be a very familiar value to you, 4/3 or 1.33. So this is the K factor. By how much, in other words, you must multiply the real Earth's radius to calculate an effective Earth's radius, so we can then draw the curvature of the Earth modified, so we can then draw the radio trajectory as a straight line. So for the mean value of n, a gradient of n, 40 units across the surface of the Earth, then we take a K value of 1.33. So K is a mean value we can use in our link planning processes when we're plotting our profile. A K factor of 1.33. So because the weather isn't stable, we're going to get changes in temperature, water vapor pressure, air pressure. We're going to get changes in N, so we're going to get changes in K. Okay? So if the K factor was 1 at my location, the meteorological conditions have dictated that the variations in air pressure, water vapor pressure, and temperature have created a gradient of 0. In other words, there is no change of n with altitude. There is no change of n with altitude. Okay? And in those instances, then, yes, the radio beam, as you can see in this diagram here, is going to be in a straight line across the surface of the Earth. There's no change in n, you see. There's absolutely no change in n, so it's going to travel as a straight line. Other meteorological conditions, which I've indicated on here, like -40, the mean value across the Earth's surface, gives us a K factor of 4.3. So there you can see the curvature of that radio signal over a real Earth. And so on and so forth. Now, what you will see is if K is infinity, so the gradient of n falls by 157 units over that 1,000 meters of altitude above the Earth's surface. If it falls by 157 units, then if you recollect the formula for the gradient, it's 157 divided by 157 minus the gradient. So 157 minus 157 is 0. 157 divided by 0 is infinity. So if K is infinity, then the radio beam will travel exactly parallel to the Earth's surface, exactly parallel. And if K is less than 1, this is the really dangerous one, well, one of the really dangerous ones. If it's less than 1, then actually K causes, the refractive conditions cause the radio beam to sag, to bend more towards the Earth, okay? To bend more towards the Earth. So this is how they're drawn in relation to the real Earth's curvature. If you want to draw the Earth as a flat Earth, then you need to bend your radio waves accordingly to match the clearance achieved in reality. Okay, so there's various ways of representing the radio trajectory. We can use a flat Earth and then modify the bend of the radio wave accordingly to match real world conditions. Or we can draw the radio trajectory as a straight line, and then we can modify the curvature of the Earth. Now, some of you will have noticed that I've put here availability requirements or reliability requirements. Those of you who've been planning links will know, we try to achieve targets of 99.99% availability, 99.995, 99.999. So can you see the lower the value of K, the greater is the refraction towards the Earth, which is, of course, going to pull the radio beam closer to objects that are on the Earth's surface. So if I cleared that object like so, just with K equals 1.33, if the K goes below 1.33, then we start to obstruct the radio beam as the radio trajectory bends downwards, refracts downwards. Now we're trying to achieve quite high availability objectives, so it would be nice to know, what's the probability of seeing a K less than, a certain value. So the ITUR have given us these figures here, which help us determine that in a temperate climate, the probability of K being less than 0.6 is less than 1%. In a tropical climate, it's 5 to 10%, so it's likely to go below 0.6 more frequently. So I already see a distinction now when I'm thinking about clearance planning, profile planning, temperate and tropical climates, there's a difference. I'm going to need to factor this in to my clearance calculations. I'll talk about that shortly. So at least I can determine the percentage likelihood of me going below 0.6. Okay, so I could feasibly take that as almost like a worst case point, K factor for where I'm planning my microwave link. Now, very briefly, just showing my age here. If we go back far enough, when I was learning link planning, we used paper like this. Can you believe it? We used graph paper like this. I'll spend 2 seconds on this, 10 seconds on this. So you would plot out your antenna heights like so on the chart here, and then you would draw the profile in. Okay, you could draw the terrain profile in here like this, and then you could draw the radio beam as a straight line. So we've actually curved the Earth's curvature, look like this. This is 4/3 Earth curvature graph paper. So it's curved graph paper for radio engineers. Okay, so we don't use flat Earth, we use curved Earth, altered curved Earth. So this is mimicking the Earth's radius multiplied by the K factor. That's what that is there. Plot the profile and then plot the trajectory of the radio beam as a straight line. And then we can work out our antenna heights. I'll leave that one with you. We've got software now. Okay, so let me move on. Now, K is not stable. K is not stable because N is not stable. So as the meteorological conditions vary, there's our standard gradient of N. And as the weather changes, meteorological conditions change. It can fall, it can rise. If it goes to there, there's no change. So the radio beam will travel in a straight line. It goes over there, that can be disastrous, and this can be disastrous down here. So we can see as this changes, then the trajectory of the radio beam will change. What that means is it'll bend more downwards, or it might overshoot our dish or undershoot our dish, or even disastrously, we can get effects like this kind of thing taking place. Now, the man in the street might say, well, if your radio connection was like that directly, and then the weather changed and it did this or it did this, well, surely you've lost your link. Now, we don't need to panic. We don't need to panic because over the page, you can see I've planned a link here over 30 kilometers. And applying some simple Pythagoras mathematics, I know the beam width of my antenna, so I can work out this dimension here at my received dish. In other words, the area over which the RF is spread in the beam width of the antenna. And those of you who've done this for a while will know that this is the half power beam width. So between there and between there, between those 2 points there, I will receive main bore power, or maybe down towards half of that main bore power. Quick, simple mathematics, you can see in this case here, and only this case, you could calculate this for all of your links if you really wanted to, but can you see that distance there, D, is actually 785 meters. So arriving at my dish, I have a circular received electromagnetic field spread over 785 meters with my very small 0.3 meter or 1.2 meter dish stuck in the middle there. So of course I can tolerate some deviation, some refraction up or down is not going to have a major impact upon the performance of my link, okay, as long as it's within reasonable limits. Okay, so don't panic, the link will still work. Okay, moving on. I now want to look at clearance. How do we determine clearance? And you might have heard this, if you've been planning for a while, you'll have heard of Fresnel zones. And I'm gonna touch on that topic now. Okay, I'm aware of time. I really do need to move on, but I don't mind overshooting. If you guys can hang around for a while, I'll just carry on. Christian Huygens, a Dutch scientist, was trying to prove how light traveled from A to B, and he came up with this theory, which is that as the light moves, which is an EM wave, of course, it'll travel a certain distance, arrive at a certain point, and he theorized that this front of the waveform consisted of an infinite number of light sources, which then radiated outwards and built up the next part of the wavefront. Okay, that was his theory, and that's fine. That's okay. Now, Augustin Jean Fresnel, him of Fresnel zone fame, was tasked with designing for the French government highly efficient lighthouses. And so he wanted to know also, of course, how light traveled. And so he said, okay, if this is my light bulb here, and this is the eye, if this is the eye of the receiver of the light over here, then if Huygens is right, then the observer will see the light arrive, but some of that light will have arrived from another source, and that source is a different path length. So the light from this source might be out of phase with the light on the main bore. So he theorized that I think we receive so much light that actually it's not as bright as we think it should, as it could have been, because we're receiving some out of phase light. So what he did was engaged in some deep mathematical thought and came up with Fresnel zones, saying that I think I can predict where these sources of out of phase light are. Any source from the edge of that ellipse there will be an out of phase source. And that's what he determined. And they're called Fresnel zones. Anything from here will be in phase, again here out of phase, but we're focusing on this first Fresnel zone. So we can relate our clearance to Fresnel zone radius. Now, there's a formula there to help you calculate Fresnel zone radius. I'm not going to go over that. Your software will do that for you. So he created lenses which blocked out those, in effect, minimize the impact of those out of phase sources by creating very clever lenses on the light over here. And of course, his light was much brighter than that had been experienced by anybody before from any lighthouse across the planet. Now, we can apply this theory to our clearance, because what we can do is say, okay, if there is an object in the way, then maybe if I make my object just clip that first Fresnel zone there, then energy diffracted down here will be out of phase energy, and energy obstructed here will be out of phase energy. So if I let that object just clip the Fresnel zone, my received signal strength should actually rise slightly. And indeed it does. So if we just clip that first Fresnel zone, then of course we experience a signal lift. And in fact, our received signal strength is actually higher than that we would receive if there was no obstacle present. Okay, by letting something impinge in the beam and just touch the first Fresnel zone, we can actually block out damaging signals, out of phase signals, and diffract them away. But I've mentioned the topic now, and I've mentioned the topic, which is diffraction. So if I go over the page here, we can relate diffraction loss to the clearance above a specific object, obstruction, on our path. But what we have to do is relate the actual physical clearance, the distance we're able to clear the obstacle by, and relate that to first Fresnel zone radius. So we calculate this, this ratio here. So for example, if I clear the obstacle by an amount exactly equal to the first Fresnel zone radius, then this ratio will be 1. And if we glance up here to the chart, let's just take any of these obstacles. A knife edge obstacle, look, is the blue line. A round earth, a smooth earth is the red line. But let's just take the knife edge, say, for example. You can see we get a slight lift in received signal strength above free space, dBs from free space. It actually lifts by 2 to 3 dBs. So we get almost a doubling of received power because we're obstructing the out of phase power. Another point of note is if we look here around about 0.6-ish of a first Fresnel zone radius and draw a line up from there or down from here, make my life easier. See, around about 0.6 of a Fresnel zone clearance, we equate to free space loss. So we can equate a value of clearance we try to achieve to a Fresnel zone radius or Fresnel zone radius. I hope that makes sense. Of course, when we go below a certain clearance criteria, if the ratio decreases, can you see we can get some serious damage caused to our received signal strength. So if we go below the obstacle, then of course what's going to happen is we are so many or portions of a Fresnel zone below the top of the object. So we put that distance there, we put into the formula, the ratio as a negative value, and we end up with a negative ratio clearance, and we can see some damage caused to our signal by that lack of clearance. Okay. So by how much do I need to clear an obstacle? By how much do I need to clear an obstacle? Well, we have various rules, various guidelines to help us determine by how much we should clear an obstacle. Now, which rules you use will depend upon the way you operate. You might have in-house rules. You might follow international recommendations by the ITUR, or you might have to follow your national regulations. And I've just noticed I've made a spelling mistake there, so I'll just change that because that'll annoy me. Your national regulations. So a general rule of thumb is that wherever you're operating, if you have any climate, any obstacle, be it knife edge or a round edge obstacle, no matter what it is, if the only value of K you can use is the median value, 4/3, then try to leave the first Fresnel zone clear. All right? Try to achieve actually objects just clipping it could be a target you could go for. But the point is, it must be clear. We use this value when you have no detailed knowledge of local meteorological conditions to help you determine the kind of sort of lowest K you might be expected to see. If you do have knowledge of that minimum K, the minimum K you're likely to see, then the ITU guidelines currently are, if it's a single isolated obstacle, in a temperate climate, you can graze that obstacle. Yes, you will experience a slight loss in your received signal strength, but this shouldn't worry you. It shouldn't damage the performance of your link. If it's an extended obstacle, like you've got a hill after hill after hill, you're going over a block of terrain that's a bit of an obstruction, then try and clear it by about 0.3 of the first Fresnel zone. If it's a tropical climate, same conditions, it's 0.6 and 0.6 in both cases. Because if you remember, in a tropical climate, we get a greater change in the value of N and K. There's a higher percentage likelihood of that extreme change indeed. However, I must stress, everybody, wherever you work in the world, please, please, please check your national regulator and the guidelines they suggest you use. And they'll be available on the license application form. They'll tell you what values to use. Okay. But they might have picked any of these values as their guidance, you see. So that's where we have to, we need to bear in mind where these figures have come from. May well originally be from the ITU. Interestingly enough, the modern guidance is to get a bit closer to the obstacle. All right, these values here, get a bit closer to the obstacle. The reason is that nowadays there are so many microwave links around each country, each nation state, and we've been using old style rules to clear obstacles by a significant amount, that what we've done is we've created far more interference than we really needed to. So we've got so much interference now that if it actually all of us today dropped our microwave links to this sort of clearance value, yes, our received signal strength might drop a little bit, but the national interference floor would fall dramatically. But it's too late. We are where we are. The original rules were set when not too many people used microwave links. If you are concerned about determining a value for K, a sort of minimum expected value, then over the preceding decades, years and years and years, the ITU have done some serious analysis of radio links all over the planet. And they produced this graph. So I know it only applies to a temperate climate in this case, but what they're saying is, you'll know the length of your link. So let's say it's a 40-kilometer link there. Look, you go up on this graph here, you look across here, and 0.75. So 99.99% of the time, it looks like the lowest K value I should expect to see is 0.75. So I've now got some knowledge of the expected likely lowest K value I will see for a significant percentage of the time. Only a small percentage of the time will it go below that value. So if I work with that value, I know I'm playing a safe game. Yeah, I'm playing a safe game. Okay. Hang on 1 second. Okay, I hope you're still with me. I'm now going to jump to, I've covered clearance, so I'm now going to take a quick look at reflection. So when we're looking at reflections, of course, it's the nature of the point that we reflect from that gives us an idea of how much danger we're in. So anything smooth and flat, and particularly wet, is a danger area. So of course, the sea is a danger area. Now, if a surface is very smooth, then the reflective properties of that signal from that point there, we call that specular reflection. Specular reflection. There's my classic postcard picture. Everything is reflected, all in phase. Beautiful picture. If this is not a smooth surface, and it's actually quite rough, a bit of rough terrain there, then the reflection will be obviously distinctly different. There'll be some scattering as well, and we call that diffuse reflection. Okay, so we've got specular and diffuse reflection. Once again, I think somebody might have a microphone on. If you could knock that off, I'd appreciate it. Once again, go back to the old days before we had software. What we had to do was take our two extreme values of K, work out our ratio of antenna heights. Let's just say it was 0.2, and then look across this curve here, and we could see that sort of from about 0.15 to 0.3 of the path length was our reflective danger area. Okay, I'll leave that with you. We don't use those things anymore because we've got software. Very quickly here, I'll just cover this rather quickly. To identify a reflection area, we actually employ some relatively simple geometry. It is really, honestly, everybody, I don't know, your mathematical ability might be absolutely brilliant. If you're a bit maths averse, don't worry about this. The software will do it for you. But to correctly identify a reflection area, you must consider the antenna heights in these equations here. You'll notice where antenna heights are considered in these equations. Look, these are the H. Every time you see H1, H2, that's where we throw it into these formulae. You must consider the antenna heights in relation to the point of interest. So if you are concerned that this might be a point of danger, you must then put in your relevant antenna heights above that surface area there to determine whether it is a reflective danger area. Potential danger. Why am I showing you this slide unless to frighten you about all the maths? Notice down here, this part of this formula here says 4 multiplied by AE. Now, AE is the modified Earth's radius. So that value AE there is the real Earth's radius multiplied by K. So when we're working out these reflection areas, we need to take into account K. Okay? So when we're working out these areas, we need to take into account K. I must stress that. It's not just about clearance. It's about determining the reflection point stroke reflection area. And hopefully I'll clarify that shortly. If you're interested, there's some other mathematics you can use here to determine the antenna heights above a sloped surface, but I won't dwell on that now. That's just another bit of geometry, really. So I'll go over the page here and let's give you a sort of a real-ish example. Here you can see I've got this sloping surface. I've worked out my reflection area point, using those previous rather complicated calculations. And there's my point of reflection. What I would do then, of course, is I would look at that reflection area and determine what's the nature of the terrain. So if that was a really smooth, flat surface, I'd be worried. If it was rocky with trees on it, I'd be less concerned. But what I've done here is I've calculated this value here with a K is for 4/3. Now, if I take the same link and then calculate that for a K equals 2/3, 0.66 K factor, which means the Earth's radius is smaller, so the Earth will bulge higher. Okay, it'll bulge higher because the radius is smaller. I'm saying the Earth has a radius 0.66, it's normal, which gives a sharper curve. So the Earth bulges up, and you can see, hopefully, that the reflection point has moved. So by scoping over a range of K factors, I can determine my reflection area. So this is for 2/3, and this is for 4/3 down here. And I can see my reflection area. Now, this is really interesting at the top left here. This is a graph I've taken from a link I've planned. So this applies only to one specific link, okay? One specific link on the face of this Earth. Don't use this graph yourself to apply to any other link. What you'll notice is across the bottom there is K factor. And along the vertical axis here is my relative receive power. So we could take 0 as a sort of normalized mean receive power. That's okay with you guys. And can you see as the K fluctuates, as the K changes, which is caused by changes in N, which is caused by meteorological changes, then can you see I'm going to experience some fades on this link? Okay, can you see that? I'm going to experience some fades, some of them down to 10 dBs. Now that could have an impact on my link. 10 dBs, you might say, well, if you've got a 10 dB fade margin and that causes your link to be unavailable, then I'm sorry, you haven't designed your link very well. And I would agree with you. A 10 dB fade margin is ludicrous. It's far too small. But don't forget, in the radio environment, we're usually dealing with a combination of circumstances. So you might get a 10 dB fade caused by reflection, whilst at the same time there's a 12 dB fade caused by maybe a slightly excessive bit of rainfall. Yes, and so on and so forth. So all these things can add together to give you suddenly a 25 dB fade, which might knock your link availability figures. Okay, so you've got to consider this, and it is well worth, when you're planning a link, asking your planning tool to calculate a series of losses, fades caused by reflection over a series of K factors, just to make sure there's no sort of weird and wonderful K factor, within a reasonable range that would cause a severe fade. Notice how they're getting worse as you go this way. Now, of course, we don't, a K of 5 or 7 is slightly extreme. We're usually operating around here and such, but, it could be the case. Okay. So well worth some analysis is that activity there. Okay, let me move on. I hope you're still with me. Now, something else we have to factor in from our reflective point is don't forget, reflective signals will diverge because the Earth is a curve. Yeah, it's convex. So if the radio energy comes down here, these black lines here, and hits the Earth, there'll be some sort of spreading of the signal as it moves away. So the RF will diverge away from that reflective point. Now that's from a smooth surface. Now most of us in the real world, most of our links probably go over some sort of real terrain. So if you apply some sort of rough terrain over this smooth Earth surface to mimic reality, then we can see not only will we get divergence, we will also get scattering. So to determine the impact of this reflective signal, we probably need to take into account the divergence, and we need to take into account the scattering. Okay. Now, our good friends at the ITU help us calculate the effective reflection coefficient of this particular point on the Earth's surface. Now, you might notice in the title of this slide, it says, and why we use software. So what we need to do is work, and I'll explain why in a second. You'll see why in a second. So we need to calculate the actual effective reflection coefficient from that point on the Earth's surface. And they came up with this rather simple calculation here. And I'll just let you know that this value here is the reflection coefficient of the Earth's surface. This is what we call a divergence factor. This is called a specular reflection factor. And this is called a surface roughness factor. So can you see they factored into the formula everything I've talked about so far? All well and good. So now I can hear you cry, where do we get these numbers from, Carl? Please tell us. Well, here we go down the nightmare road. So to calculate these values, we need to do a fairly significant series of calculations. Don't panic. So first up then, how do I calculate the reflection coefficient of the Earth's surface? Well, I need to know certain things like the complex permittivity of the Earth's surface, that value there, the relative permittivity of the Earth's surface. Some of you might remember these values from your radio and physics theory back in the day. And you might have sat in the class saying, when will I ever need this? Well, here you go. And values like this, the conductivity of the Earth's surface. And I can imagine you guys sat there now throwing your hands in the air saying, well, where am I going to get these values from? Where do I get these values from? I'll never be able to do this. Please notice the title of the slide and why we use software. Okay, why am I showing you this? Have you noticed down the bottom here? It sneaks in again. We need to factor in the modified Earth's radius. Of course we do. Because as we factor in K factor, we're actually saying that we think the Earth is going up and down as the weather changes. The reality is, of course, that it's not. It's the radio trajectory that's changing, coming closer to or further away from the Earth's surface as the weather changes. So we need to factor that into this calculation as well, okay? And then we proceed through the other parts of this calculation. I won't dwell on these, you'll be glad to hear. It gets worse and worse. But of course, before you panic, a modern planning tool will incorporate all of these values, permittivity, conductivity, and so on and so forth, which are all available from the ITU. So they'll put them into their planning tool, and when this formula is activated, then we will factor these into the calculation. So at this point, I'm going to just remove myself from these slides, and I'm going to briefly open up a radio planning tool to illustrate to you a link. So this is a link I planned. It actually goes across the sea, as you can hopefully observe. And it's 33 kilometers long, roundabout, and I've asked it to plan the trajectory of the radio wave for two K factors. You see that here on this chart, 1.33 and 0.66. Blue for 1.33, green for 0.66. Okay, and it's shown me the clearance of the edge of that Fresnel zone above the Earth's surface for these two particular K factors. So it's determined for me that this link will be okay. I've cleared the obstacle, which in this case is the sea. Now, funnily enough, I actually prefer a flat Earth and curved radio waves. If that's not intuitive to you, I do apologize. Your planning tool might actually show you a curved Earth with two different curvatures and two different straight radio trajectories. In my case, though, I can see I've got clearance. What I now need to do, of course, is check the reflection points. The planning tool shows me there are two potential reflection points. This one that's now highlighted in red, I'm not concerned about. That's not going to give me a problem. It's this one that is potentially going to give me a problem. So what I'm going to need to do is analyze that reflection point. So I asked the planning tool to analyze it for me. Reflections, analyze. I haven't got time to explain the planning tool, of course, everybody. And you can see I can pick my surface type. Is it wet ground, dry ground, seawater, etc. Or I can say, okay, it's user defined. And then it asks me to enter conductivity and dielectric constants, etc., to perform that calculation I showed you earlier. But to keep it simple, at this point here, I'll just type in seawater there. Okay. And then I'll ask it to show me what happens to my received power against K factor. And you can see on my link that I've just created, there you see variations of K factor and fades I would be likely to see for those values of K. And I can see it's not too bad. It looks like sort of around about 1.2, I might experience fades of about 8 dB, a bit more than that with a K factor of 2.8. But at least now I'm aware of what I'm likely to observe. 1 second. Okay, cheers, Ian. No worries. Okay, that will do there. Of course, I haven't got time to dwell on this, but of course, because it's oversea, don't forget, you should also factor in the tide change. You know, if this is a 10-meter tide, a high tide is going to be up here somewhere, and that might give me a different kind of problem. But we need to factor that in. We need to think about that. But for now, we'll leave that and move on to the last part of this little session. Okay, I've only slightly overshot the hour, but hey ho, who could have predicted a fire alarm, eh? I still can't believe that actually happened. So what I'm going to do is go back to my main menu here. I'm going to open diversity systems, because what I'm suggesting now is, let's say the negative impact on my power budget and availability figures of reflections is so severe, my only option is to deploy diversity. Now, there are various flavors of diversity available to me. I'm going to talk about space diversity only. With space diversity, what we're trying to achieve is the following. Using two antennas, can I optimize the spacing between these two antennas to ensure, as much as possible, that if this antenna is receiving a strong signal, we'll be receiving a strong signal, when this antenna will be receiving a weak signal. Why will it be weak? Because the reflective conditions cause these two signals here to cancel, give me a weak signal on this antenna, and at the same time, hopefully they add on this antenna. Okay. Now, if this is tidal water here, that will fluctuate. Sometimes this will cancel, sometimes that will add. Sometimes that will add, sometimes that will cancel. And what I'm trying to do is optimize the spacing between these two antennas so that when one is fading, the other one is hopefully rising, and vice versa. So I need to determine this antenna spacing. Now, once again, our friends at the ITU have given us a model to help us calculate this. And what they do is they say, okay, it's easier actually, using some relatively straightforward geometry again, to calculate the distance between 2 points of minima, 2 points of maxima, or 2 points of minima. It's easier to calculate those two. Once you've calculated those two, all you need to do is halve them. If you halve that distance, then of course, when this one's maximum, hopefully that one will be minimum. Okay, and when this one's maximum, that one might be minimum, vice versa. So when you're determining your spacing, you calculate this value, then you halve that, or indeed use 1.5 times that, or 2.5 times that. In other words, it's always an odd multiple. And that's how far we will have to space apart our antennas for optimal performance, okay, for optimal performance. And have you noticed what's crept into the formula here? Our old friend K, okay? So our old friend K creeps in, and we have to factor that in when we're calculating our diversity antenna spacings, okay? And then once we've done that, and we've calculated our spacings, and I'm going to do one more slide, okay? Then we can, and I haven't got time to talk about this, but anyway, once we've calculated our spacings, we can use formulae like this, and of course they will be buried in the software. We place our spacing there, and from this, we can determine our diversity improvement factor. I won't dwell on this slide, but I just wanted to relate it to how it fits in, okay? That's how we perform that. Okay, so yeah, people are leaving now because I've overshot the time due to the fire alarm, but never mind. So the last thing I'd like to display to those of you who've managed to stay is the following, which is go back to the planning tool, take my link here, and let's just say the link I showed you before, I have no choice. It's really badly damaged and I need to deploy diversity. So what I would do is I would deploy diversity antennas. Now, again, I'm not explaining the planning tool, but I'm just going to I'm going to activate my two diversity antennas. And I have randomly placed them 5 meters apart. I've just randomly chosen a 5 meter diversity spacing. So I press OK. Okay. Okay, I need to select an antenna. Bear with me. I'll go for 1.2 meters, the same as the original antenna. I apologize for that. I've now selected my antennas. And I can now go and evaluate my reflections again. I can evaluate my reflections again. And I can look at analyze those reflections. And I now include the diversity antennas. So I check that, that value of received power versus K again. And you can see now I've got two curves here, one for the main antenna and one for the diversity antenna. Are they doing a good enough job? I don't know. I mean, when this one dips, this one rises a bit and vice versa. But, you know, it's not, they don't particularly overlap very well in the right places. So the beauty of a planning tool is, of course, I can then ask the planning tool to optimize my diversity spacings usually, or many planning tools optimize my diversity spacing there. It's done it for me. All those calculations I've just shown you and have taken you through over an hour. It's done in a microsecond, of course. That's the beauty of planning software. And then I can now look at these curves again and look at that. Look at that. How beautiful is that? Yeah, when this one, the main antenna dips, the diversity antenna improves. When the diversity antenna dips, the main antenna improves. I've got the perfect, virtually perfect relationship between the two antennas where they compensate for each other. But as you can see, look how K factor is implicated in this, is used in this. So I get this deep fade at a K factor of 1.2-ish. But the good news is my diversity antenna picks up the slack and gives me a decent received signal strength. Okay, everybody. I appreciate, you know, I've overshot by 13 minutes. I blame the fire alarm. However, I hope it's been useful to you. I hope you found it interesting. What I'm now going to suggest is, if you have any questions you want me to answer, please ask them in the chat. Or if you've already asked them, let me know that you have, and I'll go and have a look. I shall now exit this, this planning tool. I'll go back to the main slide presentation. And please feel free to ask me any questions. I'll just go to the chat and see if there were any questions already asked here. No, that's good. That's good. We've had no questions so far. Okay, no problem. If everybody's leaving and saying thank you, I do appreciate, and thank you for your attention. Thank you for dealing with the fire alarm, and thank you for bearing with me with the delay. But as I say, if you have any questions, please fire up. The other point I'd like to mention before I go is, just let me expand this. If you do have any topics that you're interested in, please feel free to let me know. You know, you can send an email to that address there, or my email address if you know it already at Ray Castle. And if there are any topics that might be of interest to you, and if I get enough votes for a specific topic, I might prepare another one of these. Well, I am going to prepare some more of these. But if you can feed me some topics, that will help me pick one. Just related to radio, please, if you could. You know, radio planning's fine. You know, where we relate radio theory to radio planning. I'd be very interested to see those topics. Okay, I'll keep my eye on the chat to see if there are any questions. Whoa. Okay. There are questions about sharing the copies of the slides and presentations. I'll come back to you on that. So Alex has a question. As a rule of thumb, spacing the two antennas will need to be 200 wavelengths. In some cases. Yes, there used to be, when calculating diversity spacing was a very time-consuming job, as you could see, there tended to be this rule of thumb of 200 wavelengths. And I've often told people that if you're really, really stuck in calculating your spacing, you could try 200 wavelengths, you know. But it's much better if you've got a decent planning tool to help you calculate the spacing to use that to help you optimize the spacing. So you get that relationship of when one signal peaks, the other one is, well, when one signal dips, hopefully the other one is peaking. Now, also, Alex, sometimes, of course, you can work out your spacing, as you probably know if you've been doing this for a while, and then you arrive at the mast and you've said to yourself, okay, I need two antennas here 15 meters apart, and at the other mast, I need them to be 18 meters apart. And you arrive, and of course, somebody else has taken that spot. And so you're sat there thinking, oh dear, I can actually only get 9 meters apart on this one, and I have to be 23 meters apart on that one. But you can take those values across to the planning tool, put them in, and then map your signal strength graph against the K factor. And that is the great use of a planning tool. Is there no phase shift from reflection? Yes, there is, Marios. I'm going to come back to that one. Marios. If you hang around for a second, I'll come back to that. Alex has also asked a question, which is two received signals of opposite phases. Let me just deal with that, Alex, because that's another interesting point. I've just opened the planning tool again, as you can see. I'll just go back to analyze my reflections again. And let me go to this one. Yeah, this is signal strength. Okay, this is a graph of signal strength. So when the signal strength of one antenna is low, has faded by 12, notice the signal strength of the other one has actually increased by about 3 dB. Right, so the diversity combiner on the receiver will analyze those two signals, combine them, and you'll get a lift in your received signal strength, even though one antenna is actually fading. Now, of course, that illustration there is the my sort of 5 meter antenna spacing. Let me optimize again and then show you the curves, and hopefully you can see them change. Watch them change once the antenna spacing is optimized. There you go. That's better, isn't it? This isn't the received signal graph. It's a graph of received signal strength. Yeah, received signal strength. Now, I hope that answers that question. Let me go back to the chat. Okay, thank you, Christopher. Where was this one? Is there no phase shift from a reflection? Thank you, Marios. I hope you're still there. I apologize for the delay, but those two questions from Alex were linked. Actually, there might have been two different Alexes. Never mind. Okay, Marius, let me see. Phase shift. Okay, let me go back to the slides. This is very interesting. Whenever I say that about radio engineering, some people laugh, but I don't know about you, but I do find it very interesting. Let me just sort out these slides for you, gents. Sorry. What slide did I want? This is about reflections. Here we go. Yeah. And what we see is it depends upon the polarization and the angle of incidence of the radio wave hitting the surface. And these two graphs here, I've only got two. These two graphs relate to seawater, which makes sense, doesn't it? Because seawater is a danger area. So some rather interesting phenomena here. I'll take you through quickly if you're interested. If you use horizontal polarization over seawater, virtually irrespective of frequency and irrespective of grazing angle, this is the angle at which the radio beam hits the water and then bounces off, you'll notice the reflection coefficient, the percentage of energy that is reflected, will be virtually 100%. Irrespective of angle as you go across seawater. When you use vertical polarization, however, the reflective properties of the water vary dependent upon the angle of incidence, the grazing angle hitting the water. So again, another interesting use here of using vertical polarization. Those of you who've been link planning for a while may recollect that if you're planning a link that's experiencing potential to experience great rainfall loss, then we tend to aim for vertical polarization because the degree of loss experienced due to rainfall is a lot less. Over here, addressing the polarization question, the phase shift will be 180 degrees, irrespective of angle that you hit the water, if you're horizontally polarized. If you're vertically polarized, once again, we get a variation in the degree of phase shift. Okay, we do get a variation in degree of phase shift. But once again, the planning tool hopefully will factor this in and determine the impact upon the received signal strength. And you've seen it in those graphs where the signals add and you get an increase in received signal strength, and where the signals cancel and we get a decrease in received signal strength. In other words, where they're out of phase and in phase. So and once again, you see, this is a very interesting topic in itself. Unfortunately, we haven't got time to dwell on that too much today. Okay, any more questions? I think two are related to the planning tool. I'll come back to that in a second. On the ATDI software, sometimes even at 7 gigs, the spacing will be 2 meters. Would you trust this? Well, that's a recognized a professional radio link planning tool, no doubt about it. So 2 meters. Alex, what's a wavelength in at 7 gigs? Anybody got the time and inclination to work that out? I'll just do a quick calculation here. That's 300 million divided by 7,000 million. That cancels out. It's 3/70. What's 3 divided by 70? In meters. Gents, you might not believe this. I actually got a calculator out and I'm calculating 3 divided by 70. 0.04 of a meter. So that's 4 centimeters. That sounds about right. So a wavelength at 7 gigs would be about 4 centimeters. Okay. So you've got 200 centimeters. So what's 4 into 200? That's about 100, isn't it? No, it's about 80. What's 4 into 200? For goodness sake. Carl, what's happened to your maths? 50. Sorry, I'm laughing because I couldn't believe I couldn't calculate it. But so you're about 50-ish wavelengths apart, and that might be enough for that link to work successfully. Yeah, Alex. Okay. Now there's a question there about how long is the session. The full link planning course is 3 days. Actually, it's 3 days. 4 meters, 4 centimeters, correct? Yeah. Okay. Okay, everybody. I'm happy to hang around and answer questions. I really am. I really enjoy the topic. If there's anything you want to ask me, please feel free. If not, we'll close down the session. And my colleague Paul will probably dive in now to close it. But if you want to send me some more questions in chat, please feel free. I'll just ask Paul to close the session. I'll mute myself now, Paul, so you can take over, and I'll act.
Yep. Thanks, Carl. Really interesting session there, and well done for coping with the fire alarm break. As Carl mentioned, if you're interested in a more in-depth look at microwave link planning, we do have the full course running at the end of October. It's running as a live online course from the 25th to 29th of October as 5 half-day sessions. Go to our website, raycastle.com, for details of that. Our next live webinar is on 5G new radio, and will take place on the 12th of October. Again, find details of that session on our website. I'll be sending a recording of the session over to everyone who registered for the event within the next sort of 2 or 3 days. So look out for that if you want to review the material that Carl went over today. But otherwise, thank you for joining us. We'll see you on the next one. As Carl said, he's going to hang around and answer some more questions in the chat box if any come up.